And good evening, everyone, and welcome to Starry Nights Live, streamed from the SFU Trottier Observatory. And if you're joining us here, spending your Friday evening with us, then you're a nerd, which means you're our kind of people, and we appreciate you. I am Matthew, and I'm joined tonight by Kyle. Hello, Kyle.
Hello, hello. How are you, Matthew?
I'm doing very well. I think there are some people in the chat who are mentioning it's been a long time since we've been looking up at the sky and actually being able to see stuff up there. So
Oh
that is pretty cool.
my gosh, it's been too long since
Too
we've
long.
been looking up. I am so ready for this.
Ready? Yeah, we're not seeing any clouds up there, which is pretty good. We're getting into that season, so that's pretty awesome. Joined in our moderation chat for tonight, we also have Rohit joining us from out in Ottawa, I believe, so in the future. So he can let us know what's going to happen in the next 3 hours. And we also have Julia, so thanks to them. And I believe we also have some volunteers from Rask tonight who are always a welcome addition to the team. But because I am terribly disorganized, I don't think I have the email as to who's actually joining us. So if we have Rask members tonight in the chat moderation, please make sure that you introduce yourselves and tell us what you're doing and how you're feeling about life. So, what should we start with? What are we looking at first? I heard there's been an object of particular notoriety in the news lately.
Yeah, and I think we broke a record. I think a couple weeks ago here, there were some four lovely humans that made quite the camping trip, I think, in quite a advanced vehicle that they made a journey. I think it was like Artemis.
Artemis, yeah, it wasn't a cow, although I heard they could travel over the moon. But yeah, so here we've got
yes, that's true.
We've got the moon queued up here. So there we are. Hooray! Oh, it's drifted a little bit. I'm gonna move us a little bit more center and target here. Did you watch the Artemis launch? I'm guessing you watched the Artemis launch.
I was glued to the live stream. Oh my gosh, it was so amazing. I was just after teaching for me, I was watching the launch, and seeing that launch was such a cool moment with the SLS system, and it was flawless. And seeing the ship like break the sound barrier and seeing the curvature of the Earth and going over, it was great. It was great.
Oh yeah, it was amazing. There was also, I saw a couple of these videos that were posted by people that were on planes. And so you could, like, they were near Florida or whatever, and you could see the thing taking off and passing them. And it was like within seconds they're at the altitude of an airplane and then heading up into space. It was wild.
Yes. Oh my gosh, that was so cool. They'll remember that forever.
There you go. I was watching it with a bunch of people. We had a launch party at the H.R. McMillan Space Center, and I think there's about 200 or so people that joined us down in the auditorium. It was really cool being able to watch it there because the planetarium itself opened the same summer as the moon landing. In fact, it opened in anticipation of the moon landing. It was one of the reasons why it was constructed in sort of the Apollo and early rocketry heyday. So to be able to watch it there at this place that had such a history of the moon era, the first time we had gone, was really cool. There were people there were so emotional, and of course people were crying, and and watching this thing go up into the air, and of course very very much hoping that it was going to this time because it had been delayed for the previous 2 months. And then I think it was a day or two later, and they were almost had arrived at the moon, a 4-day journey more or less to get there, and I was picking up the planetarium's portable planetarium that we take out to schools. And I rolled this thing out because I got to get there pretty early to get to schools in the morning. So I roll the thing out and I look up in the sky and there's the moon. And I'm thinking, wow, I'm standing at this place while the moon is in the sky, and I'm one of the few staff in all of these generations of staff that can be here while there's actually people out there again. And I just thought that was such a neat thing to be able to do and to experience with so many people again.
Such a nice moment. I mean, I was watching it with the live stream with my mom and dad a few days later, just checking in on the crew, seeing how they're doing, and it was so cool to just talk with them and just acknowledge that my parents saw the Apollo missions.
Yeah.
Right. And now they're watching, like they were watching the Apollo missions with their parents, and now they're watching the Artemis mission with myself, and seeing it as quite a generational connection there.
Oh
I
yeah,
think that was really, really cool to
yeah,
experience.
like civilizational connection. It's
Yeah.
that this was such a big feature of our civilization. So many decades ago, and here we are going
Mhm.
back. Now, so one of the questions we've been getting often about the moon and this most recent mission is like, why are we going back to this place that we have already been to before? And of course, there are a number of objectives. One of them, though, is that if we're looking right now, we're seeing some of the craters near an area of the moon we call the terminators. This is the distinction between where the light side and the night, or light, I say dark side. The moon doesn't actually have a dark side, but what we're meaning is that the daytime and
Yeah,
nighttime
fair.
side of the moon. And you can see that around here, where I've got the arrow, you can see the shadows inside of these craters. Well, at the south pole of the moon, there are craters there that, because of where they are positioned on the moon's surface, light rays from the sun fall almost parallel to the ground. And so as a result, they are called PSRs, or permanently shadowed regions on the moon, which never receive any sunlight. And radar that has been bounced off the surface in those areas show that there are lakes and lakes worth of ice inside of those craters. And what we're hoping is that that water that has settled there and formed ice might have captured volatile chemicals from the early days of the solar system. So trapped in that ice, you might actually have a preserved state of the early solar system, which helps us to understand better its chemical makeup, and maybe even how water was deposited on Earth in its early days as well.
Hmm. Absolutely.
And I think one of your favorite
And it's
tidbits.
really neat to think.
Oh, sorry. Go ahead, Kyle. Go ahead.
Oh, no, no, sorry. Just saying that's it's so cool to think about that. Just water is also coming to be quite common throughout the solar system. Like seeing
yeah.
observations of Mars where it looks like there was flowing water on there at some point. And now detecting water on the moon, and of course water here on Earth, and it's like it's pretty common around these parts, I think, eh?
Which is awesome, right? Because if water is truly something that's needed for life to exist, or the chemistry of life as we know it, the fact that we have started to find so much water, and now this kind of primordial water, even on our own moon, is amazing. And then, of course, if you know your water chemistry, water is hydrogen and oxygen. So if you find it in a place, you can also split it apart. And so water can be water, it can be air, and it can also be fuel. And so if we are trying to travel to other parts of the solar system in the future, the moon might be our launch off point to do that. Well, one of the things I'm most excited about is that if we can use the moon for future astronomy observation, because as cool as it is to be putting people into space, we can always see much farther through astronomical devices like telescopes. And the moon acts as a natural blocker for Earth radio signals. So our Earth is very, very noisy. It gives off a ton of radio noise that's beamed out into space. But if you could put telescopes on the far side of the moon, especially radio telescopes, the far side of the moon is a radio shadow for the Earth. And out there, we might be able to listen to the very, very, very faint signals of the cosmic microwave background radiation, which is left over from the Big Bang, which means we might have more insight into the very beginning of our universe. So the moon might help us to better understand the formation of our solar system. It might even be a key to helping understand the formation of the universe itself, which I think would be very, very cool.
Absolutely. I'm just so excited for potential moon base in later Artemis missions, and seeing what kind of science and advancements in technology could be spawned from these.
Yeah,
these
definitely.
missions.
A quick note on that too. I'll say I've been reading a really interesting book, and I recommend it. It was very. I have found it very sobering in light of our recent space exploration missions, and it's called Astrotopia, and the author is named Mary Jane Rubenstein.
Ooh.
And her view on the moon, and there's a whole chapter in this book, and it's called "The Rights of Rocks." And so it says, and one of the things it asks is like, what right do we actually have to be changing the wider solar system, especially if we take into consideration the ways that we have treated our own planet. And so it's considering like, should we be protecting certain sites on the moon, not just heritage sites because we have been there, but actual formations on the moon, rocky features, craters. Is the moon really something that we are allowed to do with as we please? Or is it something that along the rest of nature should actually be preserved? And I thought this was a really good question. So these are things I think we should be thinking about in anticipation of going there.
What a time to be alive to actually
Ask
seriously
these questions.
ponder
Yeah,
these questions,
I know.
right?
Yeah. Astrotopia. I'm going to put the name of the book in the chat here. Now, I know one of your favorite things, Kyle, to point out here is that you can tell certain dimensions of craters by features inside of them. And I was wondering if you wanted to chat about that a little bit. I can maybe zoom in on some of the craters here while you do that.
Yeah, sure. Okay, so even from this image here, you see it's, of course, speckled with all sorts of craters. Now, if we zoom in a little bit more, and just one thing to mention just before I continue on, the waviness that you see there is definitely, it's natural. It's just due to the heat, like residual heat from the Earth during the day that's kind of manipulating the light that's coming towards us, right? Almost like looking at a highway on a hot summer day, right? You see these waves that go across the surface, right? So similar thing, it's all good. Well, not totally all good because it interferes with some observations, but nonetheless. Anyway, so you see some of these craters have a softer or more dull edge, and some are sharper. Now, these are indicative of how old these craters are. Now, even though there's pretty much no tectonic activity on the moon, other impacts from the moon or from asteroids hitting the moon and things like that will shake things up occasionally, right? So it kind of dulls the edges over millions and thousands and millions of years, right? But again, most recent craters have sharper edges. Now, the size of them, you can estimate based on there's central mountain features. Now, there's one prominent kind of the center right. There's kind of a larger crater with almost like a little peak in the middle there. Also in the center top left place. Now, those peaks are due to these asteroids that are so large that they hit at such incredible velocities that they liquefy and heat up the rock, right? All that energy has to go somewhere, right? Conservation of energy. So it disperses into the rock and almost makes it lava and liquidy, right? So just like a drop of water on a still pond, there's like a little bloop and almost like a little drop peaks in the middle. So the same kind of thing happens. And typically these central peaks only form with craters that are about 100 kilometers across in diameter or larger, right? So it's really kind of cool. And kind of a neat little lesson on physics there, where if you hit something really, really hard, it hooks it. Liquefies it.
Imagine seeing an impact like that, actually being able to bear witness to one. That would be amazing. And that's kind of what the moon does, right? The moon is like a record keeper of these impact events, and is therefore almost like a timekeeper of the solar system, or like a time vault that we can think of as a record holder of the solar system. Yeah.
And I think the Artemis crew actually saw some small impacts when they were going to the far side of the moon.
Oh, amazing.
Make the orbit around. And some of the scientists on Earth were giddy with that kind of stuff.
Oh, I bet, yeah.
Speaking of which...
speaking of which...
They probably took a crap ton of pictures. Let's have a look at them.
Yes, I got some of them here that I thought were really neat, that we can look at them. And you've probably seen some of these in the media already, but I thought it was worth kind of taking another look at them. So, I mean, look at this picture. Oh my goodness, how clear that is.
Oh my gosh. It kind of looks like, what was the zero gravity plushie that they take? Was its name Rise?
I didn't know that. Is on this mission on Artemis, they took a plushie with them?
Yeah. I think it's on every mission. They bring a little zero-G tester kind of thingy, and usually they open it up as NASA opens it up as a contest where students and the younger generation can submit their ideas. And the one that made it onto Artemis was named Rise, and it's pretty much the moon with a little baseball cap on that's supposed to represent the crescent Earth.
Amazing.
And, footprint on its back. Like there's so many hidden little gems on Rise. It's really, really cool.
That is awesome. Wow, that's so great. Yeah, and of course, the Earthrise photo, the original one that was taken back in 1968, was taken by Bill Anders during Apollo 8. There's actually a quote from Anders on our moon bench outside of the observatory. So if you're ever at the observatory the next time that we're there in person, there's a quote from Anders, and it basically, I'm paraphrasing a little bit, but it says, "We went all this way to explore the moon, and in turn we discovered the Earth." Right, looking back on our own planet. And I think that's important because in some ways that's true, not just scientifically or literally looking back on our planet, but I think it gives us a sense of place in the wider universe, and those who stepped foot on the moon, calling it, I think Buzz Aldrin had said it, the magnificent desolation, like this beautiful but desolate place compared to this jewel that is our own world floating in the universe. There's another one here that's closer up, so let's take a look at that one. This was the one that kind of blew up on the media.
Yep. And I think the Artemis crew took their phones with them onto the mission, so they definitely made lots of posts on Instagram when they landed, and seeing a couple of them where they're just jaws are on the floor with their recording the Earthrise here from their phones is really kind of funny. A little piece of modern technology that they took with them, right? So
yeah, because I think this might have been, I don't recall now, but I think this actually might have been one of the pictures that was taken literally just with a phone, like with an iPhone. Imagine looking out the window and this is your view out the window. I mean, astonishing. I got one more, and then there was another one that was captured that was actually a very unexpected picture. So first of all, look at this one. This is one more that's kind of neat looking out the window. And look at that. I mean, wow.
Incredible. It's like you can cover it up with your thumb.
Yeah, and that was one of the things that the astronauts said they could often do, just like cover the whole world with your thumb. I remember there's a homage to that in the Apollo 13 film with Tom Hanks covering it up. Tom Hanks, of course, also narrating now one of the films that you said you're coming to see at the planetarium. So I'm glad that you're doing that. Thanks for coming.
Oh, I can't wait.
Great. But then this photo was captured. Now this is probably one of the most amazing photos that will ever be captured by humanity. And so, first of all,
so much to this photo.
There's so much going on in this picture. So first of all, this photo would not have happened unless the mission happened exactly when it did. So remember, we had planned originally of launching in February, then March, and then we went on April 1st. Much to the chagrin, I'm sure, of moon landing deniers. But here we are, and the things lined up just the way that they could in order to take this picture. So first of all, there's a couple dots here in the photo. This over here, I believe, is Mercury. This is Mars.
I think it's just here, Matthew. I think that rightmost star you're indicating was just off the.
It might have been off the screen.
Frame.
Thank you. I'll move it over here.
There we go.
There we go. So yeah, over here we have Mercury. This middle reddish one is Mars, and then over here, I believe this is Saturn, and then we have the moon here. And so there's some weird stuff going on here because you would expect if the moon is obscuring the sun, and remember, light in space is not like light on Earth. On Earth, light gets scattered by atmosphere. There's no atmosphere in space, and there's no atmosphere on the moon to be able to scatter light either. So if we're obscuring the sun like this, we're eclipsing the sun with the moon, why are we still seeing any features on the moon's surface? And it turns out that this is because of Earthshine. So this is from the light from the Earth hitting this side of the moon. And then I thought this was a composite shot because typically when you see images like this of bright objects like planets and moons and stuff, you don't see stars. But because the moon has eclipsed so much of the sun, you're still able to see stars in the picture. So this is crazy. And someone saw, and this is there was very little processing done in this photo. So this is like straight, this is not photoshopped or composited. This is literally just straight, pretty much out of the camera.
Incredible.
So that is a cool picture, and it would not have happened the way it did unless we had gone when we had. So pretty cool stuff. Would you go to the moon if you had the chance? What do you think?
Oh, do you know what? I think I would, but it's one of those things where because I keep trying to picture myself in space, and I'm going, what's the closest feeling that we have to being in space? And think back to a swing set.
Yeah.
Just as you're at the crest of a swing, like in that fraction of a second before you come back down, that's essentially what you're feeling all of the time,
All the
for
time.
days and months on end. And I'm going, I don't know if I can handle that. Maybe, but I think I might be able to stomach it if I could go a lap around the moon.
Yeah.
And then I'm back on Earth, and I'm like, do you know what? I did it. I have my my conversation topper, so to speak.
Yep.
And I'm good.
Yep. Oh, that makes sense. Yeah. And on this one too, I think it would just be like, what would I be able to see on the mission? Like,
Yeah.
what things do I look forward to? And one of them on this mission was, I believe this was something I didn't know. It was the first time that humans saw the far side of the moon with the naked eye, which didn't happen in the other missions. Even though they did pass around that side, it was in pitch blackness. But because of the way that the light was falling on the far side of the moon during this mission, humans for the first time did see the far side of the moon with their own eyes. We see the side of the moon all the time with equipment, but it was the first time we'd seen it with the human eye, and that is pretty amazing. Something never seen by anybody.
So many firsts.
So many firsts. Well, what do you think? Do you want to move on? Should we move to, I think, what's next on our
Yeah,
list?
we're gonna be a little ambitious for this stream.
Yeah, what are we doing?
What's
the
first
plan?
time back in a while,
Uh-huh.
and we got we got Jupiter lined up, I think, right? To
Okay,
have
yeah.
a look at.
All right, let's do it.
And then we're going even further beyond with some
Whoa.
deep sky galactic objects. Ooh.
Oof. And sometimes deep sky
see how we do.
we were going to see how I do. Sometimes deep sky and especially galaxies are a bit of hit or miss for a couple of reasons.
Mhm.
One, we do have the moon in the sky right now, so it does tend to sometimes overpower more distant galaxies. And also, it is a bit of a tech glitch, but I guess it's something interesting to talk about in terms of science. So if I move over this window here so that you can all see it, I've got some stats and stuff that I've hidden because they're not as fun to look at as the pretty pictures. But we have a camera on the telescope, of course, which is taking images and things for us. And right now, one of the issues with the camera is that we have a cooler that's on. And typically this will cool the camera down to lower temperatures that are needed in order to get rid of a lot of the noise and fuzz that is sometimes in these pictures to get really long exposures of faint distant objects. And we noticed today that the temperature is not coming down on the camera. That might not affect us at much. I just kind of brought it up because it's interesting just in terms of how the photography is done. So the noise in a camera can introduce a lot of extra fuzz. And since you have a lot of darkness in space, you want that darkness to be as clear as possible. So that might interfere a little bit today with our ability to take some deep space images, but it might not at all. So we'll see what happens. We'll see. We're going to keep, and if not, we can always pivot and go to some brighter stuff. So for now, let's head over to Jupiter.
Jupiter. Oh, is there a mission on the way to Jupiter right now?
Oh, there sure is. Yeah, you want to talk about it? I forgot about that. That's of course we should.
Kind of
talk
a
about that.
leading question, yeah. It's the Europa Clipper mission is on its way, and I think it's a flyby of Europa, I believe, right?
That is correct. Yes, and if I understand correctly, it is the largest space probe that we have ever built. It is very big.
Ooh. We didn't know that part. Okay, yeah. Because now the reason why Europa is so cool is it's covered in ice, essentially, right? We're talking about water all the time. Like we talked about potentially water on Mars, water on the moon, water here. Well, Europa is very, very interesting because there's a surface layer of ice, and because of its proximity to Jupiter, when it goes about its orbit, it kind of lengthens a little bit and then contracts due to the tidal forces of Jupiter. You get closer to something, you feel a little bit stronger pull of gravity, and that length and contraction will kind of induce a little bit of friction. And so there's some hype that maybe there's a global ocean underneath Europa. So Clipper is on its way to Jupiter to kind of take some images, seeing if there's anything interesting. And there could be a follow-up mission to land on Europa and take some potentially core samples, essentially, just like what scientists do in Antarctica.
That's
Little
amazing.
ice core samples and analyze it. So really, really cool. Really, really interesting stuff. And of course, Juno is orbiting Jupiter in a highly eccentric orbit to analyze the clouds and to see what kind of interesting chemistry and things is going on there, as well as analyzing storms and weather patterns and fluid dynamics, things like that.
That's
So
amazing.
Jupiter's really cool right now.
Jupiter is
Yeah.
really cool. Yeah, and think about Europa. That the crust on that moon is 10 kilometers deep, and there might be an ocean underneath it that's 100 kilometers deep. So there literally might be more water under this moon than on the entire planet Earth.
Yeah, and I think the Challenger Deep, which is the deepest part of our planet, is, well, it's taller than Mount Everest, or sorry, deeper than Mount Everest is tall, which is, well, 26,000 feet, but in metric, I think that's like 3 or 4 kilometers, I think,
Wow.
or more than that.
Imagine we did find something swimming around down underneath there. Space fish, space turtles,
Space fish.
space
Yes.
whales. Maybe something unlike anything we've ever seen before.
Space
I
whales.
think I think the understanding is that if we did find life under Europa, this is one of the other things about by the way, everyone's like, what are we looking at right now? I think because I've been doing so much manual moving around the moon that the telescope became uncalibrated slightly. So whenever I was pointing to stuff, it's not there. So I'm just doing a recalibration of the telescope's tracking position so that we can kind of get back on target. So in case you're wondering what's going on. So right now the telescope is, it has millions of little magnetic sensors inside of it so it knows where it is. So it doesn't actually see the sky. The telescope itself is kind of blind to the sky. It knows where it's pointed because of those magnetic sensors that are in its base and in its motors. So I'm just realigning with those magnetic sensors so that it has an idea of where it's actually pointed again. So just bear with us for a moment here and we'll get back to things. I lost my train of thought. What was I talking about? Europa. Oh, life. Okay,
Europa.
so if we do find life on Mars, and this is a crazy thing in and of itself, it is possible that because Mars and Earth share material with each other, that if life began on Mars, it might have come to Earth or vice versa. So even if we do find life on Mars, we might find out we're all Martians, which is itself pretty awesome. That would be an amazing thing to learn about our lore and origin story. Because Europa is so far away, it is quarantined from life in the inner solar system. And so if we do find life there, we know it's a guaranteed second, we say, genesis of life. But that would mean that if life happened twice in the same solar system, then we could probably make an assumption that it is quite common. So it would be amazing if we did, find life in Europa in some form.
Oh, and maybe we'll be alive when that discovery is made. I'm hopeful.
How long till, how many years until it gets to Jupiter in this case? Do we know?
How what?
The Europa Clipper, how many more years until it gets there? Like 3, something like that?
Oh shoot. Yeah, 3 or 4 years. Yeah.
Amazing.
On its way.
On its way.
Had to do a couple flybys and loop-de-loops around the solar system in order to
just for fun,
get
just
out
for like
there.
for giggles.
Yeah.
Yeah.
A little scenic route.
Little scenic route.
Mm-hmm.
Okay, so we have rehomed the telescope. So now we're going to reconnect it to the software that controls the dome. By the way, the software that shows us the sky is called The Sky. That is the name of the software. And what you're looking at here, this shows where the telescope is pointing. So the yellow dot over on the side, this slit shows where the dome window is. So if you ever have been in the observatory and you've seen the window moving around, this is it here. So this is where the wall is, and this is the actual aperture that the telescope is looking through. So I'm waiting for them to resynchronize with each other. And then if I've done my job correctly, we'll find Jupiter, and it should be in the center of our field of view.
lovely eye on the sky.
The funny thing is, it might be easier for you to just go outside and find Jupiter right now because it is the brightest thing above you in the sky right now.
Yes, I mean, I was just outside about an hour ago, and I saw Venus in the western sky, and the moon directly above me with Jupiter close by. So quite a good line we had this evening. So, but I think Venus is a little bit too low right now still. Unfortunate.
Is that Jupiter? I might have found Jupiter. Let's see. It looks like our targeting is still a wee off. But let's move things over a little bit.
Lining orbital trajectories. I do see it there. Definitely.
Yeah. It's unusual that it's
moon.
usually this far off. I'm going the wrong direction here. I'm going to go this way. There we go. Come over here, Jupiter. There we are.
Oh, there it is.
There it is. That was a move.
There's the king. 3? I thought there were 4.
One of them might be either in front or behind, I would say. Oh, there's one.
That is true.
Over there.
Oh, there it is.
All right, let's turn the exposure down more so we can actually see some of the actual planet. There it is. Hooray!
Success. So again, yeah, we had to reduce the exposure time here because Jupiter's so big, it reflects a lot of light back to us. So so we don't overexpose the camera. We have to turn down the exposure time there. If
I think we can see a red spot. Is that the red spot?
mistaken-
I think it is.
Yes,
Right there?
I see that.
Yeah. Yeah, that's the one. That is the red spot. Look at that. That's awesome.
It's really cool. Oh, maybe some keen observers here. Isn't the Great Red Spot supposed to be on the bottom of the planet? So why is it on the top?
Oh, why is it on the top? What's going on, Kyle?
Well, the telescope that we have in the observatory uses mirrors to reflect and focus the light that comes in. So what happens is when that light comes in, it hits our primary mirror and gets focused to a point. That's where kind of the secondary mirror is, which further bounces it back down and goes into the eyepiece. But through all that travel, the light essentially flips. It's almost like, I know you guys have done this before, looking at a spoon concave side and you see your reflection is upside down. It's the same kind of principle here. So there's that flipping of the light. So that's why through the telescope here, a lot of our images and things are actually flipped.
And you might notice that the planet looks a bit fuzzy, and I know sometimes this happens when we're looking through the camera or through the eyepiece. People are like, well, I've seen pictures of Jupiter, and they typically look sharper. And that's because when you get images of planets, it has gone through a process called lucky imaging. And so, Kyle, you were mentioning earlier that when we're looking at the moon, we could see it kind of wobbling and waving around. And you use that really good example of like hot air coming off of a road. What that means is that when we're imaging from the ground in the Earth's atmosphere, when you're looking like this at a planet, it's wobbling in and out of focus. And there are these moments when it'll be in focus, and that's the lucky image. So what we'll do is we'll actually videotape a planet like this to do a picture of it, and then we'll spit out all the frames from that video. and then we'll find those few frames where the planet actually is in focus, and then we layer all of those particular frames together to make a very crisp image of the planet. So if you've seen pictures of Jupiter from Earth and they look much clearer than this, that's because they've been processed using that lucky imaging, whereas right now we're just watching like the live feed that we're getting through the planet's atmosphere.
They also mix together some exposure frames as well, because I think if you were to expose the light on just Jupiter, just like as we're seeing now, we might not be able to see the moons. So you kind of have to play with the balance of the light essentially during the processing. So you kind of get enough light that you can see the moons and pretty stars in the background, but also seeing the tremendously bright features that Jupiter has. So you kind of reduce the exposure there a little bit. So kind of a lot of processing that goes into these photos.
And if I turn up the brightness here, we said earlier we could see those moons. So there are the 4 largest moons of Jupiter that we know as the Galilean moons, so called because they were viewed by Galileo, and he noticed that they were moving around. And so part of what made us think that maybe we were not at the middle of the solar system is because these smaller moons were orbiting around Jupiter, and Galileo thought, well, maybe that means the planets are actually orbiting around the sun, and this is kind of like a mini solar system. And of course, the Jovian system is a system. It contains, I think, how many moons are we up to now? 90 something or other. It's almost 100 moons. But these are the 4 largest.
Yeah, I thought it was 100.
Yeah.
That's what I thought.
So if we look up, let me look up where the moons are right now.
Yeah, I think a lot of those moons, before Galilean moons are large enough that gravity pulls them into a sphere. But almost every other moon in the Jovian system there are captured asteroids. So it's like little pieces of rock that happen to float by. Jupiter's so big, so they kind of pull or get pulled into an orbit around Jupiter. And that is technically the definition of a moon, a smaller astronomical body orbiting a larger one. And that's why Jupiter has so many freaking moons.
Yeah. And this one here, I just looked up. I'm like, where are they? Which ones are which? So right now, this is Europa. So this is the moon right here that you're looking at that might have life somewhere else in the universe. So you're looking at it right here, right now, live at Starry Nights. That might be where there's something swimming around in our solar system outside of our own planet. And that is pretty cool.
Oh. Could you imagine they would have these life forms might have bioluminescence? So it might be like another star field when when a probe gets down there.
Or you actually imagine you can see the light shining by something under, like through the ice, like where the ice was thinner, and you're some ship on the surface, and you see some, like, I don't know, some Leviathan type creatures swimming. I don't know if there's macroscopic creatures on, in Europa, but just saying how cool that would be. Anyways, yeah, some kind of bioluminescent whale. I guess not a whale because they got to breathe atmosphere and there isn't there. But you know what I mean. Megalodon, space megalodon.
Yeah. Sure. Cool. Sure, some astrobiologists will have some theories.
Yeah, maybe they would. Yeah, maybe you don't need bioluminescence. I don't know. But out there, it's also very dim, so maybe you do under the oceans of Europa.
It's true.
Do you want to try moving on to some galaxies? I'm feeling a bit nervous. I'm gonna be honest because it looks like the telescope's targeting is a wee off right now. And then we've got the moon and stuff. But if this doesn't work, we'll try a couple galaxies, and if it doesn't work, we'll switch up to some brighter star clusters. How does that sound?
I'm game.
Okay.
Let's engage the warp drive.
Let's engage the warp drive. Okay, so why don't we I know we have our list of galaxies here. I was thinking, because I know this one has worked before, so maybe as a test galaxy, we can do Cigar. Want to do the Cigar galaxy first?
Sure.
Okay, let's try that.
Let's do Cigar, a nice palate cleanser here.
Okay, So what I've done is I'm changing the settings now on the camera. We're going from, because we were looking at bright objects, our exposure time on the camera is just a few milliseconds because we don't need to gather a lot of those juicy photons into the camera. But now that we're switching to this galaxy, so Cigar is 23 million light years away, so we're just getting the little faintest kind of drizzle of light from this galaxy, so we need to expose longer. Actually, we've already gone into long exposure, so you can see how that's not working here in this case because we're overexposing Jupiter, although it is a pretty cool picture. All right, so let's move on to a different target, and we're going to find the Cigar Galaxy.
And Matthew just touched on this, but to give you guys a little bit of context for the size scale that we're kind of jumping to here. The moon. The first thing we saw, of course, is our closest neighbor. It's about 380,000 kilometers away. Light takes about a second to get there, so pretty quick. It's fine. Jupiter is about 750 million kilometers away. So light takes about between 45-50 minutes to get there. Okay, so you're seeing Jupiter almost an hour ago. Was an hour ago. Now, we're jumping to galaxies, which are millions of light years away. And 1 light year, is about 9 trillion kilometers. Okay? And that's pretty much the reason why astronomers have talk about these distances in light years. Because eventually, if you're using kilometers, you're going to be writing so many zeros on your papers and notes that the distances become meaningless. So we're kind of using time as a distance measurement, which is kind of paradoxical if you think about it. But a light year is how much time, or the distance that light travels in 1 year. The Oort cloud, which is pretty much the edge of our solar system, is about or 1 light year away in terms of the edge of the Oort cloud. That's essentially how far our solar system's gravitational influence kind of reaches here, right? So now we're in the millions of light years, so this is going to be crazy. And the reason why we're so nervous about having the moon out and bright objects like Jupiter and things is the photons that are reaching us from galaxies, there's very, very little of them. And that's why we have to crank up the exposure time so we can see. So, wish us luck. Wow. Pretty good star field we got going on here.
There are some stars. That's something.
And confirm. There are
stars. Now, to be clear, those stars are in the Milky Way. Those are in the foreground. We're trying to find a distant background galaxy. But I am worried that maybe we might still not be completely on target here. So, what I'm going to do, if you all bear with me, we are going to turn. So I was stacking. So we did something called a live stack. So we're taking faint images and putting them all together in like a light sandwich to make them bigger. So what I'm going to do is just to make sure we are on target, I'm going to find a bright star and make sure that it is in the center. So what was I looking at earlier?
Yeah.
Let's find Polaris.
Polaris? Isn't that the North Star?
It is the North Star. At least it is a brightish star. We should be able to find it in the field of view.
If you're ever lost in the woods, no phone, no Wi-Fi, no nothing, look for Polaris. That's north. You're good. Using a technique called star hopping, you can use the leading stars in the Big Dipper to kind of draw a straight line to Polaris. Really quite cool. And that's a technique astronomers use as well, star hopping, to get to different
places,
different objects point of view. Yeah. Pretty neat.
Let's try a different one. All right, classic fancy red star of Arcturus, one of the closest red giants to our own planet. The red should be very clear, and then we'll know that we were in the right place.
Yes.
But I'm looking, if it were similar to Jupiter, it looks like targets are slightly off to the left of where they're supposed to be in the field of view right now.
Yeah, if you do like a little touch to the left, maybe I'll put it in the center.
It might, yeah. Problem is, though, with the galaxies, they're so faint that it's hard to know that they're even there at all. So let's see. First of all, is the dome out? It is. There it is. So we can see up here, that is the star, and it should be here. So we're a little bit off. Okay, so here's what we're going to do. If you could bear with me, we're going to do one more recentering of the telescope, because sometimes that's just what it takes. So we'll turn the domed connection off, because the recentering the telescope, we don't want the dome to be chasing the telescope around right now. So let's move it one more time. And you can probably see in our in the stream, you can probably see the telescope moving to its different areas. If that is still running. Oh, there we go. I might have.
Yep.
Okay, there we go. So you should probably see the telescope moving around inside. Man,
Seeing behind the scenes.
Since we're here,
stuff.
Here is a process completed image that we did of the cigar galaxy. When in doubt, here's one that we already did. I'm not. Did you work on this one? Did you do? Have you done cigar? Or which images have you processed?
I have not.
But
unfortunately,
you've probably done data collection for some of them, though, right? Sometimes we just
I've done
sit
data
down.
collection.
Yeah,
yes,
yeah,
absolutely.
Yeah, and so Joanna usually is really good at bringing some of that data collection home. But yeah, so this is the cigar galaxy, and this is after. We won't get it to look like this. This is one of the images after it's taken on our main astrophotography camera. Usually a few hours of exposure time, and then post-processing that the computer will do to filter out more of the atmospheric distortion and highlight the colors. But we should be able to at least get the shape of it if things go right. So let's see here.
Mm-hmm. And yeah, and maybe you guys noticed that it looked like a pretty straight-looking toothpick. That's because we're seeing it edge on. So if you were to imagine galaxies as like a dinner plate, right? And in space, there's really no directions like up, down, left, right, top, bottom, that kind of thing. So galaxies are oriented every which way. Sometimes they're oriented face on. So we see like the beautiful spirals and barred spirals, and we really get to see some definition and structure to them. Other times they could be edge on, just like this the cigar galaxy here, and that's much you're seeing it just the way it sounds, where it's almost like you tilt that dinner plate so it looks flat from your perspective. So usually it can be kind of tricky to try and solve any kind of definition or structure from edge on. But sometimes astronomers can pick out information using the Doppler effect and seeing how it rotates as well as looking at the different speeds of the stars when they do that. Looking at the speeds and trying to pick out which stars are moving faster or slower in that dinner plate, essentially. So, kind of cool. And there was a little bit of a stream, like nebulosity going through the center of it. So sometimes galaxies will have streams of nebulosity and star formation, which can result from colliding with another galaxy, or maybe it's newly formed, things like that. And I think in this particular case, it is the result of a galaxy passing through Cigar, if I'm not mistaken.
Yeah, and I believe also because of of gravitational interaction with M81, the neighboring galaxy. Which one's that one?
Yeah.
Yeah.
Hmm. Yeah, so it's pretty cool to see some of that stuff.
Oh, Bode's galaxy. That's what I'm thinking of. Yeah. Okay.
Oh, that's the one.
Yeah.
Hmm. Ooh, okay. So when we get it here, just to give you again, sense of scale, Cigar Galaxy is 23 million light years away. So you're seeing it as it was 23 million years ago. Which is incredible.
I love that. That it's like fossil light. You know, this is like in the background.
Yeah.
And that is pretty awesome. Okay.
And it's almost like, so yeah, you're seeing it as it was 23 million years ago, but it's vice versa as well. If we were on a planet on in the Cigar Galaxy looking back at Earth, we would see ourselves 23 million years ago, which again, modern humans haven't evolved yet.
That's wild.
So seeing Neanderthals and things walking around.
I thought there was an article I saw recently, and it was like, how big would a telescope actually have to be in order to look back and see dinosaurs on our planet? Like,
Whoa,
that could see
okay.
the Earth from a distance of, say, at least 65 million light years away. And the telescope would have to be something like, it was like 4 light years wide. It was insane.
Holy smokes. That's insane. Well, I mean, okay, to take the brilliant pictures that maybe some of you have seen, looking at the central black hole, Sagittarius A of the Milky Way, and M87, used the Event Horizon Telescope Array, which is a series of telescopes strategically placed, all over the Earth, to communicate and link up with each other to make an Earth-sized telescope, right? See these beautiful pictures and things. So if you want to see smaller and smaller things in the sky, you have to make bigger and bigger telescopes.
Okay, I think what we're going to try doing is we are going to switch to the primary camera, the main astrophotography camera. Is what we are going to do, and see if we get a better chance trying to find targets, because it has a wider field of view, so it might be able to pick up the objects, given that we are having some alignment problems with the telescope here. So we're going to close this camera out, and we use different software to run the primary camera. It's called Maxim. Get that over here.
Maxim to the rescue. Yes, and once again, please feel free to drop questions in the chat. Our lovely moderators are waiting to hear your curiosities.
And
we love keeping the conversation going.
Here's something cool. We have a cluster of cameras on the outside of the telescope. So if you ever come to the planetarium, you'll see that there's like a ball of cameras that we actually have to swap between in order to run them. So right now we're using the camera called the ZWO, which is our kind of live stream color camera that we use. It can see in all the colors of the light spectrum simultaneously. What we're going to do is switch over to the QHY, which is our main astrophotography camera. So this like light you can see has switched from here to here. So the camera has like, we physically rotated which camera is now seeing through the light port on the telescope. This camera doesn't see in color at all. It just sees in energy. Think of it that way. And instead there's a filter wheel in front of the camera that determines which light color is going to be allowed through to hit the sensor. And so it's a monochrome camera. It just sees in black and white, and it's just knowing that it's detecting light. Which light it is, it doesn't care. The filter has just determined like, oh, this is now red, this is now green, this is now blue. And then usually we have to mix the colors together afterwards in order to get it. The reason why we do that is that a normal camera splits each one of the pixels in the camera into 4 different colors. You got one red, two green, and one blue. But if you want the full maximum resolution of your camera, you want to be using every single pixel for every single color. And the only way to do that is to switch which colors are coming in each individual photo. So in this case, what we're going to do is just image with the luminance filter, which is all the light allowed through, but the camera won't know which colors they actually are. Let's see. So let's get that set up. And Joanna might come in and help to do this because I have not ever used this camera on this piece of software yet. And so here we go.
So good to be back talking about space.
No kidding. On this camera, the coolers are probably working, so we can already see the sensor temperature is like dropped below 0 degrees Celsius. If it's similar to our last main camera that I have more familiarity with, this one. This is our new fancy astrophotography camera as of about a year ago. We were able to cool the sensor on that one down to minus 40 degrees Celsius, which is pretty incredible.
Minus 40. That's crazy. In that little black box. So now we're seeing some of the
I see
stars
the galaxy.
There.
It is there.
There's the galaxy there.
So now we're going to move our point slightly. But we're getting something. Now, this is a very short exposure that we've done here. That's why it kind of just looks like this is mainly noise that we're seeing here in the picture. But this is just a very quick exposure just to see if we're on target, basically, is what we're doing. And this camera is much more sensitive than the previous one. So it will give us a better idea of whether or not we're on target. And you're just seeing us troubleshoot in live time. This is what we have to do sometimes when we're trying to image or doing science or any kind of experimentation. Sometimes things don't always go the way you think they're going to, even when you've just recently tested them. And so you're seeing us troubleshoot live using the tools that we have. And that's what science is. That's just what science is.
Mm-hmm. Hey, we're human. I like being human. I like learning. I like making mistakes and doing better.
That's right. That's all we can ask, you know.
Mm-hmm.
The galaxy up to the left here that you're seeing, the upper left, that is Bode. So that's the neighboring galaxy to the Cigar galaxy. This, of course, is just a representation of it on our sky graph. That pink square, or sorry, the purple square that you saw as we were zooming in, that square shows the field of view of the telescope. So sometimes if you just want a general sense of how an object is going to look like, in the field of view of the camera, then you can zoom in here, and that purple square shows you what everything will generally look like to scale based with the telescope. The field of view of the telescope is measured in arc seconds. And so the field of view square of the telescope is about 60 arc seconds square.
Mm-hmm. Oh, to give you a sense of how big an arc second is. Okay, so imagine you held out your hand and you stick out your pinky. The width of your pinky, held at arm's length, is 1 degree of sky. Okay? Now, each degree is further split into 60 arc minutes. Okay, so we're thinking about even smaller. And every 1 arc minute is split into 60 arc seconds. Okay, now the reason why we say arc all the time is, of course, from our perspective, the sky looks like a giant dome, right? So we have to kind of, when we're dealing with coordinates and specific locations, we have to say this arc stuff because kind of feels like it's on a curved surface, right? Kind of similar to coordinates on a map on Earth, degrees, minutes, and seconds, that kind of thing, right? So we use the same kind of coordinate system in the sky.
Think of it as like a rotating sky, and the rotation of an arc, literally an arc. Yeah.
Second of arc.
Second of arc. Now, one of the things that Joanna is adjusting here right now, you can see there's maybe it might be slightly off screen from what we're seeing, but let's see here. Oh, I'm sorry, Joanna. Here, I'm moving the mouse on you. I'm trying to see what everyone's seeing. So let's see. Can I? What if I do this and then move this? No, that doesn't work. Okay, that's okay. So it gets slightly out of frame here, but basically Joanna is adjusting something called the binning on this. Actually, Joanna, if you want to move the camera control window just to the right a wee bit so that the audience is able to see it when you get a chance. Just zooming in here. There's the galaxy. But the binning is a collection. It's actually putting groups of pixels together to make what's called almost like a super pixel. What's the advantage of doing that? You're trading off resolution because you have overall fewer pixels that are now represented in the picture, so fewer dots. But by combining the dots, you're getting a brighter image. So what you're doing is essentially you're trading resolution for brightness is what's happening. And so that's kind of what's going on here right now is we are trading a little bit of the resolution of the image for brightness. And usually for an object like a galaxy, you can get away with that because a lot of the galaxy is kind of nebulous. It's more of like a cloud. And so that cloudy galaxy, you can kind of sacrifice some of the resolution for it because it's never going to look very crisp or sharp. But if you're looking at something like the moon's surface, you're probably going to want all of that detail, and so you'll drive the resolution up, and you don't need the additional brightness because the moon is already very, very, very bright.
Yes. Oh. Mm-hmm. But so you can see here, I'm just noticing in the chat. So once again, the Cigar galaxy is 23 million light years away. So that's incredibly far away. And you can see a little gap in there, right? In that dinner plate. So if you remember the picture that Matthew showed a little bit earlier, there's like this little bit of nebulosity that was going across the dinner plate, according to my analogy. You can see that here with that little bit of a split right in the center. So kind of cool seeing that kind of stuff. You can see a bit of structure too.
Yeah, that actually looks quite good.
Yeah.
You'll notice that if you look at the very center of the galaxy, it almost looks like there's a little bit of like an X shape sort of toward the very middle there. We think that that prominent X formation is actually likely the result of two giant swirling disks of material orbiting the central black hole at the middle of that galaxy. And so this galaxy does have a black hole in the center, like many do. One of the reasons why there's this formation and also this galaxy is so bright is that that black hole is likely feeding on material, kind of similar to what Kyle was saying, that the galaxy is being disturbed by neighboring interactions. And when that happens, it causes material to fall into that central black hole. Our black hole is pretty much dormant now in the center of our galaxy. We have one, like Kyle was saying. We linked all those telescopes around the world in order to take a picture of it. Our galaxy's black hole, Sagittarius A, looks like it might have had a snack at least about 30,000 years ago. And we know that because when you take images of the center of the galaxy, there's these two big lobes of accelerated gamma ray particles that are coming up, like energy from these lobes of gas that are being shot off from the middle of the Milky Way. And so while our black hole isn't active in that it's not feeding constantly, in which it gives up energy, black holes are like messy eaters. So imagine that while they're munching, they're kind of burping energy all over the place, or it's kind of, nothing comes out of the black hole, but it can accelerate the particles around it and sometimes spill them out into space. And when that does happen, sometimes galaxies can be affected by that central black hole. We don't know whether or not that would harm life that was developing in a galaxy. It sometimes can stunt star formation because the energy traveling out from the rest of the central massive black hole can do something called squenching, I think it's called, where it can slow down the rate of star formation in a galaxy. But our black hole is not nearly as active, and maybe it was a long time ago. We seem to see that in earlier galaxies. So again, as Kyle was saying, when we see a galaxy that's millions of light years away, we're seeing it millions of years in the past. And we do see galaxies that are billions of light years away. They seem to be more active in those early stages of the universe, likely when there was more raw material circling around the centers of those galaxies. And that might not happen so much in the present era, except when those galaxies are bumped or nudged or disturbed by a neighboring galaxy, in which case some of the leftover material will then spiral down and toward the center. But yeah, this is a pretty good image of the cigar galaxy.
Yeah. And I just want to acknowledge good catches from our chat members and moderators. Cigar is 12 million light years away. My apologies. Whirlpool is about 23 million light years. So a little bit closer.
That might be my bad. And when I was throwing together notes last minute for the day, so apologies, everybody.
You're okay.
It's amazing that we can even measure the distances to galaxies at all.
Exactly.
Yeah.
Still really cool stuff, but yeah, good team. Thanks for the catch.
Thanks for the catch. If those of you who don't know, there's one of the most important pieces of research to help us measure the distances to galaxies was done by an astronomer named Henrietta Swan Leavitt. She created something called Leavitt's Law, where she recognized that certain types of variable stars that change in their luminosity over time can be used to measure distances across space. And those were the types of stars that were then used by Edwin Hubble to measure the distance to the Andromeda Galaxy for the first time, proving that other galaxies even did exist, because we weren't sure if the structures that we saw, like this galaxy, were in our galaxy or farther away. And Hubble did mention that credit should go to Henrietta Swan, but unfortunately, like many women of that era, their their accomplishments in astronomy were not noted. So that's something to remember, that there are many women whose stories weren't necessarily celebrated at the time, who have contributed to our understanding of the universe.
And I think and another notable figure is Vera Rubin as well for discovering dark matter.
Yeah.
Another tremendous contribution to astronomy that went unnoticed for a while. Oh, long while. It was so fascinating what she found, because thinking about how things move in space when they're orbiting another object, the further out you go, the slower that you move in order to maintain an orbit. Our planets do that. Mercury, of course, travels the fastest in order to maintain its orbit, completing a cycle in a matter of days. But the further you go out, it turns to months and then to years, right? Although, when she took some data looking at stars orbiting a galaxy, she found the contrary. Seems like stars were orbiting at the same rate, no matter how far away they were. So, which is what led her to conclude that maybe there's some invisible matter that's kind of pushing the stars faster and faster, the further they are away.
So
This
I think
mysterious dark.
mysterious, and we still don't know what it is. Although there are some pretty cool people that are trying to figure out what it might be, and it might make up the majority of all the matter in the universe. We're the weird stuff of the universe, Kyle. You and I, because we're actually visible.
Mm-hmm.
So
Absolutely.
yeah, that's right, and all of you. So we're going to move on to another galaxy. I think we have one more exposure coming in. So we are adding right now. This is, I think this is a stack we're doing right now. We may not be stacking them together. Anyways, we're doing about 60-second or 20-second exposures right now of the galaxy. We're going to move down to whirlpool. So that's the whirlpool galaxy. Beautiful, almost the opposite in its orientation to this galaxy. So like Kyle was mentioning, we're looking at this
Yes.
galaxy edge on. Whirlpool, we're going to be looking almost directly from above or below, depending on which way you think of it. And Whirlpool is also in the process of interacting with another galaxy. So kind of very similar situation to this one, except we're looking at it from a different vantage point. Whirlpool also, notably, was the first light image of the telescope. So when the telescope was constructed and opened, we opened it to the public in April, but before that, in the March of 2015, the first target that we ever imaged was of the Whirlpool galaxy. So this is kind of a full circle moment here, in a way, seeing Whirlpool, which is itself a full circle from this vantage point where we can see it. So there you go.
Absolutely. Hold on. I just wanted to circle back as we're kind of going there, talking about the distances again, because it's actually quite fascinating, the different steps that we take to measure these distances. So Matthew mentioned the variable stars. Okay. That's where we're measuring the distance to galaxies and things. But to measure the distance closer in, we use almost like a little parallax method, so to speak. So imagine this. You are driving down a highway and you notice that the trees are moving faster than, or appear to move faster than the mountains in the background. Right? That effect is called parallax. So if we were to take a picture of a set of stars in our sky at one time of the year and then wait 6 months so that the Earth is on the other side of the sun. Take that same picture, and we notice that some stars might have shifted ever so slightly, which is really quite interesting. Almost like if you stick out your thumb and then rapidly blink your eyes back and forth, you see your thumb apparently moves. And from fancy trigonometry and math and physics, you can figure out the distance to these stars. However, that comes at a limit. Eventually, when you're trying to figure out the distances to galaxies, you stick out your thumb and you blink your eyes back and forth, but you're trying to measure the distance to a skyscraper behind your thumb, compare that to another skyscraper, and there's not much change. So you have to think of or come up with another way to measure things, and that's where Cepheid variables come in, which is really quite cool. Even farther beyond that, looking at galaxies that are billions of light years away, you have to look at supernova, which is stars blowing up, which is a whole other thing, which is crazy. Type 1A supernova, to be exact. Now this galaxy looks incredible.
That is a great shot, and that really gives you a sense of how powerful our main astrophotography camera is at the observatory. This is just after a few seconds of exposure, and look how much structure is in there. I'm almost convinced that next time I do this, I might forego the color. I mean, that's a sacrifice, right, in the short term. before being able to process the image, you're sacrificing a lot of the color that we can show all of you that is in the galaxy, because there's a lot of beautiful colors in this galaxy. But you get this much structure and detail in it. Wow, look at that. That is incredible. That is amazing. Holy smokes.
That's great. What's right next to it? Is that other?
It is another galaxy. So yeah, these are basically, the whirlpool is an interacting galaxy with another galaxy, and so we're not sure if the neighboring galaxy here has passed through whirlpool once already. That might be a possibility, or is on its way in. So I think there is some debate as to what direction the companion galaxy. But the companion galaxy, if it has passed through the main disk of whirlpool, it was probably about 500 million years ago, and there are plumes of gas that extend from this galaxy to the companion because of the tidal forces or the gravitational forces that are pulling at it as well. This galaxy is the one that's about 23 million light years away. So thanks again.
Yes.
And so yeah, we're looking at it from this angle. This galaxy has also been studied pretty intensely by the Hubble Space Telescope. So you can see it's one of my favorite images by Hubble of this galaxy that just shows like how powerful that telescope is as well. And one of the things that we've learned here, that we're privileged to learn as staff that work here at the observatory, is how to process the data from pictures like this. But once you've learned how to do that, and if you're really interested in doing it, it is a bit of a process, but once you get used to it, it is really fun. You can take raw data from almost any public telescope and process it on your own, including data from the Hubble Space Telescope. So if you want, you can literally go and take data from the Hubble Space Telescope and reprocess it as your own images. Of course, you got to give credit as to where the data originally came from. But some of the most beautiful astrophotographers are people that are processing data off these giant, huge telescopes that are just open and accessible to the public. And that's one of the cool things about public funding of space missions, is that data then becomes the property of humanity for us to be able to learn from and practice with and better appreciate the universe around us. And I think that's a really cool thing. That's why science is so amazing. It's something that connects us to the universe, but I think ultimately as well with each other.
Yeah. Yeah, all this data is publicly available. Like, you can find exoplanets, you could find supernova. It's the sheer amount of data that's being collected from all of these beautiful instruments is too much for just the select astronomers that are looking at it, right? So that's what's really great, is they post this stuff. They go, hey, you guys are clever humans, try and help us out.
Help us out, yeah, because we need the brain trust, the public brain trust. Yeah, absolutely. There's a question I saw in the chat. It said, I thought it was good and relevant to us discussing distances in space, but it was what is the name of and what is the closest star to us? I'm presuming next to the sun, and that is Proxima Centauri. So by comparison, this galaxy is 23 million light years away. Proxima Centauri is 4 light years away. 4 versus 23 million. And even then, at the speed of our fastest spacecraft, a journey to that star would take 75,000 years. So we're just talking to another star. And so I think this is also important when people say, oh, well, we'll search for exoplanets and we'll find another one that's like us, and that could be the next place that we inhabit in the future. And that is just not going to happen. So for now, limited to the velocities that we can travel, our best bet is to just make sure that we keep our own planet habitable. And that's the lesson we learned by looking out into the cosmos.
This vast cosmic sea is quite grand, but I think it's in our nature to explore. And we're just dipping our toes with Artemis, with Mars missions. It's cool to be like the pioneers in these kinds of missions. It's so cool.
Okay, we're going to see if we can squeeze in one more galaxy here, maybe even 2. So another one on the list that we had was the Sombrero galaxy. Sombrero is cool because it is another edge-on galaxy. But it's got this really kind of distinct rim around the outside that makes it look like a sombrero floating in space. So we're going to see what that one looks like. And again, thanks to Joanna for jumping in here to run the main camera. If you have the opportunity when you're visiting us for Starry Nights, Dr. Joanna Wu is the head professor that runs the observatory, and her research is actually on galaxy formation. And so if you ever have galaxy-related questions and you happen to be joining us at Starry Nights in person, make sure to ask Dr. Joanna Wu on her thoughts on galaxy formation. So we got a little bit of a glimpse of what Sombrero is going to look like here in the field of view. And there's its dummy picture that's here as a placeholder in our Sky software. And so Joanna is clicking off of the target, as you can notice, just to compensate right now for our targeting issue. So we're probably going to have to recalibrate the targeting measurements that the telescope is using right now to find its position in the sky. And every once in a while, it does need to be updated sometimes. But wow, look at that. That is amazing, actually.
That is so cool.
That actually kind of blew away my expectations of what we're going to see for galaxies tonight, so I'm pretty happy about that.
Yeah. I was caught off guard a little bit. I was going, okay, we set the bar.
Yeah, I'm like, I know I'm supposed to be saying stuff because there's people watching, but I kind of just want to stare at this picture, to be honest. I think, you know what, galaxies are my favorite celestial objects. They are just so beautiful. And we live in one. And if you were ever in a dark enough sky, you can go and see the actual Milky Way. And it is a tragedy that right now 2/3 of the Earth's population can no longer see the Milky Way galaxy just because of the light polluted skies. But if you're around here or in the Lower Mainland, there are a few places that you can go that are dark skies preserved. One of them is McDonald Park. Also, if you get out to toward Hope, Manning Park is a really good place. One of my first pictures of the Milky Way I ever took was out at Manning Park. And then even on the road out toward Whistler, if you find some dark spots, you can even usually see at least some of the Milky Way.
Yeah, I think Porto Cove is definitely a good one. Oh,
wow.
Look at this.
Holy smokes.
This.
Look at that.
Like a lighthouse in a misty lake.
That is amazing. Holy smokes. It's like a UFO.
I want to launch. Yeah, that too. I want to launch off what you said about just galaxies being like an awesome object to look at, because I also like them because of their potential and of what they could hold, right? It could be teeming with life that are looking back at us and imagining what the same things that we're imagining, right? And it's just that potential and connection that, we might not know each other exists, but at least we exist in each other's imaginations.
Totally. Yeah. In our imaginations. I love that. It's a very romantic thought. That's really cool. Yeah. At least we exist in each other's imaginations. Wow. You should write that down, man. That should be on a wall quote somewhere. Oh. I love that. That's really good. I once one of the coolest things I ever got to do was I got to hang out and interview Dr. Jill Tarter, who was one of the founding members of the Search for Extraterrestrial Intelligence, or SETI. At the time, she was working at the Hat Creek Radio Observatory in Northern California that SETI uses to listen to the night sky. There is a whole valley there. It was one of the best night sky views I've ever seen because it's isolated from light pollution and, of course, also radio noise and radio pollution to be able to pick up signals from the distant parts of the universe that might be trying to communicate with us. And she let me sleep overnight under the dishes. So we were there all night under the dishes. I took a time lapse of the Milky Way moving over top of them. There's 42 of the dishes, by the way. The answer of life, the universe, and everything.
Mm-hmm. Just like in Contact, right?
Yeah, exactly. Those big dishes. Yeah, exactly. Pointing up at the sky.
That's so cool.
Yeah.
That's so cool.
In fact, the Ellie Arroway, the character in Contact, is based off Jill Tarter in real life. And there are pictures of What's the actor's name now? Off the top of my head. I should know this. Come on, who's the actor in Contact? Okay, I'll look this up quickly. Maybe
There's Matthew McConaughey.
Yeah, I know that. Yeah. Come on. As soon as I see it, I'm going to be like, of course. Jodie Foster. There you go. Jodie Foster.
Face.
So,
there we go.
There it was. So there's pictures of Jodie Foster with Jill Tarter in her office. She has a picture with her, and it's like signed and everything, which is awesome. Anyways, the point of all this is that she said a couple really profound things like that too. Like she was saying, I would like to think that when I look up into space, what if our star is part of the constellations in some other creature's sky? And they're looking up at our star, wondering about the planets that are orbiting around it. And maybe they're just discovering, from the wobble of our star, the transits of planets in front of it, that there is like a gas giant, Jupiter there, and then finds Earth and whatever else. And but when I asked her why she did this work, she said, I want to know that technological civilizations are actually long-lived, that we can survive without blowing ourselves up, that we make the healthy choices. And if two of those civilizations are able to detect each other at the same time, then that would seem to suggest that they can make it, that we can make it. And that's what she wanted to know.
So incredible to talk about. And I think a lot of movies are definitely picking up on this optimism as well, and it's so heartwarming to see that in media.
Oh yeah, Project Hail Mary. Did you see Project Hail Mary yet? It was a great movie.
Project Hail Mary. That's what I was trying to reference.
So wholesome.
Fantastic book. Yeah, so wholesome. We're not going to spoil anything. You just have to go see it.
You gotta go see it.
It's super incredible.
Super wholesome.
Yeah, gotta go see it.
Okay.
All the emotional beats, just like in the book. It's an amazing looking disc.
Okay, we're going to see if we can squeeze in one more. I put in a request for Sunflower Galaxy. Oh, by the way, we didn't really talk about Sombrero, so what's going on with this? So this galaxy is 31 million light years away. It is one of the most massive objects in the Virgo galaxy cluster. So that's a galaxy cluster that we belong to. It's about 800 billion solar masses altogether. The Milky Way is about 1.5 trillion, so it is quite big. So that is a big galaxy. But it is smaller in diameter than us. It's about 50,000 light years in diameter. But it does have an unusual number of globular clusters. So we've got these big clusters of very old stars that kind of orbit around the galaxy. They're almost like, think of them as like moons of the Milky Way, but they're big clusters of stars. And it has 2,000 of them, whereas the Milky Way only counted about 200. So for some reason, this galaxy contains about 10 times the number of these old clusters of stars than ours does. And I don't think we exactly know why.
I mean, Joanna's hot on the trail.
Okay, the last one we're going to do is called the Sunflower Galaxy. And this is one of my other also favorite shaped galaxies. And I have in the past tried to image this one with the previous astrophotography camera. But I was unsuccessful, and I don't remember why. I think there was a lot of haze in the sky that night.
Hopefully it's better tonight.
Yeah, well, we're having a lot of luck so far.
Light and everything, but
also, this is a far more powerful camera. The mirror is cleaner than it was last time I tried to do this, because that could affect things too. We clean the mirror now more frequently. In the past, we once went. It was almost 10 years, I think, before we cleaned the telescope mirror the first time, and it was really dusty. It doesn't physically obstruct your view. It's more that it just diminishes the overall light and contrast of the pictures.
In fact, you'll see a couple more like these little ghostly circles in the image. I don't know if any of you caught it, but just when when Dr. Joanna Wu was adjusting the brightness here for Sombrero, there were a couple of these shadowy dark circles, and those are little motes of dust that are on the mirror that we had.
Yeah, we had to clean off,
focus out.
Totally. Mm-hmm. There was a question. I think is this about my keyboard? Question: what keyboard are you using? It sounds very creamy. Well, thanks. It's an ND75 mechanical keyboard. I love it. It was a gift from a friend of mine, And this one actually happens to be, because the friend who got it for me wanted to make it space themed, so a lot of the keys on the keyboard are actually Apollo themed. So my enter key, for example, has the Saturn V rocket on it, which is pretty cool. So there you go.
Oh, that's cool. That's so cool. I love that description of it's creamy.
Yeah. How do you clean it? How do you clean the mirror? That's a good question. So there are professionals that have to come in to do it. The mirror is very, very sensitive. In fact, we were having this conversation earlier. Kieran, one of our other staff, was saying that like the coating that's on the mirror is very fragile. So any kind of like touching or impressions on it can leave permanent damage on the mirror's surface. And so what ends up happening, and I've never seen it done myself, but my understanding is the way that it works is you basically spray a fluid on it. The fluid kind of turns into a film, and then you lift it off, and it basically peels the dirt off the surface, so there's no rubbing or any kind of abrasion or damage that's done to the mirror. And it requires a professional, so you have to have a professional that does that. And so we might not have a lot of time on this one because I know we're at the end of the stream, but let's try to get we might be able to get at least one or two little exposures here and see if we can get some detail on that galaxy.
Sneaking in. I would be so nervous if I was in that position. Holy smokes.
Oh, there it is. Look at that. So
that's looking neat.
This is cool because rather than being edge on or above, it's kind of like on a side. So you're basically looking at it kind of like from in between all the other galaxies that we've looked at. But I love the structure on this one. It's cool. There's no bar on this galaxy, and so what I mean by that is that in the core of the other galaxies, you might have noticed that the core itself looks more like oblong rather than circular, and we call that a central bar in a galaxy. Our Milky Way, we believe, has a bar, so it's a barred spiral galaxy. This galaxy does not have a central bar. Its radius is about 55,000 light years. Again, the Milky Way is somewhere between like 100 to 150,000. But it does have this large gas structure around the outside that has been measured to about 130,000. And it is approximately, and someone could double check me on this just to make sure, 25 million light years away from Earth. So it is one of the these other galaxies that is about the same distance from us and has this really kind of neat, almost like pillowy kind of shape to it, like that I really like.
Mm-hmm. Kind of looks like there's some like a concentric circle there, like
almost, yeah.
There's like a brighter circle in there, and then a more dimmer disc around the outside. So, kind of interesting.
That is another really great photo. I am glad. Thanks, Joanna, for stepping in. This was a pinch hit because I thought our night was kind of messed up. I wasn't sure. I was touch and go there for a bit. Yeah. Gotta be honest.
That was fair. A little heart beating there as well, but this is looking really fantastic. Great structure in the arms. In the disc, I should say. Yeah.
Oh, that's really good. Cool. Well, listen, everyone, we'll probably wrap things up there, but thanks so much for spending. We always enjoy this so much, and so, just let everyone know, we appreciate coming and spending your Friday nights with us and just letting us talk about something that we love so much and be able to share it with all of you. And remember that we do this in person every other Friday of the month. That's not the last Friday of the month. Last Friday is this.
Yes, every other Friday but the last one of the month. Just to say it again.
Just say it again. Last Friday of the month is streamed online. Hey, and if you know people that also might be interested, but they're not here, I saw someone who apparently was in Missouri. Thanks for joining us. That's amazing. But if you know I know, that's crazy. That's awesome. But if you know other people that might want to join us, but they can't be here in person, they can always join live. If you are, though, in the area, please make sure to come join us on Burnaby Mountain on Fridays that are clear. So clear Fridays, we are not open if we think it's going to be cloudy, and we usually make that call somewhere between 12 and 1 p.m. So if you follow our social media, we are on X, we're on Blue Sky, we're on our Facebook page, and there is a mailing list you can sign up for as well, and that will let you know whether or not we're going to be open on a given Friday. And then come on up. Remember, it's free. There's other telescopes from Rask. Awesome. Good shout out again to Rask. Kyle, you're part of Rask. What does Rask do on Starry Nights? How does that help us out?
Well, we set up telescopes. They bring up their own, even loaning from the club, and we're so open to just letting you or letting everyone look through the telescope, what they're seeing. You know, sometimes in the observatory, we're looking at two or three objects in a night, and but they're looking at everything else, right? So it's one giant star party. They always appreciate and love hearing questions and curiosities from you guys, and plus you get to see the wide range of instruments and telescopes that are used, right? Some are refracting telescopes, other are reflecting telescopes. Some are big, some are small, and you get to see a whole range of what they can see, depending on the sizes. So it's great. It's great. They love it up there.
Oh,
I
it's
love
amazing.
being up there too.
Yeah, it's
And just,
literally
yeah, it's
one of the best things ever. Like, it's such a good vibe. All of you make that amazing. So please come and hang out with us. And of course, thanks to Rask for making that possible as well. Royal Astronomical Society of Canada, by the way. We always just say Rask, but that's who they are. And you can sign up and become a member with them too. So that's something else you can do.
yeah,
I think it's
absolutely.
there. Any last words of wisdom, thought, or inspiration, Kyle?
Uh, just keep looking up, and what I love to do is on a dark, dark night, just go for a nice, quiet walk, listening to the soft, quiet breeze at night, and just looking at the immense star field that lies above you, you know. And that's kind of, I feel, the heart of stargazing is just pull up a blanket, lay down, put on some music if you want to as well, and just look at the night sky and appreciate the place, our little nestled oasis in the universe.
Love it.
And maybe someone else might be looking back.
Okay, someone's gonna be looking back. And I'll repeat the words of one of the smartest and wisest young little people that I ever met. Once, when I was doing a grade 4 show about the Earth, and I asked them what makes the Earth habitable, and they said, love is what keeps the Earth habitable. And I agree. So, everyone, keep loving each other, love the Earth, and we'll make it out there in the universe. All right, have a good night, everyone, and